Okay, ladies and gentlemen, so welcome to this small tutorial about the vector random variable. Okay, so here what is a vector random variable? So basically, it is just a collection of some random variable putting together. Okay, so in particular here, so we let the S to be a kind of array which contain n different random variables. So S1, S2, Sn. Okay, so each of these is a random variable, and then depending on different situations, so this random variable can be independent or maybe dependent. And then here what we are going to do in this tutorial is, so we would like to develop some basic theory about that. Okay, so in particular, how do we study the distribution of this vector random variable, and so how do we study the expected value, variance, or stuff like that. Okay, so which is something that we do for the single random variable case. Okay, now so here then let us try to do that one by one. Now and then of course given, so just recall what we have learned for the single variable case. So let's say you got a random so let's say when you got a random variable s, okay, so which is just a single random variable. Now and then in our elementary probability course, so given this random variable s, then we will try to study the distribution of it, right? Okay, so what is the likelihood that so the s will take certain value or take certain range, and then of course after that, so we will also talk about the expected value, so which is the average value of the random variable, and then of course the last thing definitely will be the variance, right? Okay, the deviation of the s from the expected value. Okay, so here, okay, we will try to basically do the same thing on this vector random variable. So how do we define this distribution, how do we define the expected value, and how do we define the corresponding variance? Okay, now then let's try to start the first thing. Okay, so the first one definitely will be what? The probability distribution. Okay, now and then here just remember, if you only have a single random variable, so how do we define the probability distribution? So remember there are two ways. So let's say if this is a discrete random variable, then we try to describe the distribution using this probability mass function, so which is what the probability that s equal to s, right? Okay, and then in case if it is a continuous random variable, okay, then we will what? Try to describe that using the probability density function. Okay, so which is fxs. Okay, but of course as you know, so this probability density function does not really represent the physical probability of of s, right? Okay, so let's say, okay, if we want to know the probability that s is between a and b, okay, then here using this probability density function, then you can get this probability by integrating this PDF, okay, from a to b, right? Okay, so then this is what we do for the single random variable case. And then actually for the vector of random variable, okay, so let's say you have n-dimensional random variable, then actually we can try to define the probability distribution in the same way. Okay, so basically we will try to make use of what we call joint density function. Okay, so again, just like the case for the single random variable case, so we can try to define it in two different ways. So let's suppose if all the xi are discrete random variable. Okay, so that means all these are discrete random variable. Then here, then you can try to define the joint density as this probability mass function. So which is what probability that s1 equal to s1 equal s2 equal to s2, and then sn equal to sn, right? Okay, so which is parallel to the case for the single random variable case. And then similarly, if you have the if all the si are continuous random variable, then we will try to define this what we call the joint density function. Alright, so which is fs and then s1 and then up to sn. Okay, so this is again, this is similar to this probability density function. Okay, and then again, given this, so if you want to find the probability that the random variable s1 lies in between a1 and b1, and the s2 lies between a2 and b2, and then sn lies between an and bn. Okay, then here, then you can try to similar to the single random variable case, then you can get this probability by evaluating this multiple integral. Okay, and then ds1 dsn. Okay, so then this is how do we get the probability by doing this multiple integral. Okay, now and here just give you some so to just give you a little bit example on this. Okay, so let's suppose if I got let's say if I got a we got two random variables x and y. Okay, and then such that the joint density function is given by this. Okay, and then the x and y can be any non-negative number. Alright, now and here let's say I want to get the probability that let's say the s is between 1 and 2. Okay, between 1 and 2, and then the y is between 1 and 2 as well. Okay, then here if you want to get this probability, then you just derive this interval. Okay, so you just try to integrate this PDF, okay, respect to s and respect to y respectively. Okay, and then here because you are asking for the s is between 1 and 2, so that the upper limit and the lower limit of the inner interval will be this 1 to 2, and then for the y, okay, again it is also between 1 and 2, right? So that the lower limit and the upper limit for the outer interval, which is the one for the y, will also be between 1 and 2. Okay, now and then the last thing is just you try to evaluate this integral. Then of course the last thing is then you can substitute this PDF. Okay, and then you do this multiple integration. Now and then to evaluate this, so first of all you first start with the inner integral, okay, which you integrate with respect to s and keeping the y fixed. So in that case, so what do you get? And you get this stuff. And 2 and 1. Okay, now and here you can just put in this, and you get okay, then this is how do you do the this inner integral, and then the next step is you try to integrate this. Okay, so respect to y. Okay, then this one is easy. Then you will get this potential mass y plus 1, and then 2 and 1, and then plus potential mass y plus 2, and then you take 2 and 1. Okay, then you just punch in the 2 and 1, and then you can get the final answer. So I guess I'm not going to do the details. Okay, now so here then this is well, the basic idea of evaluating this playing with this joint density function. Okay, now and then after this, then after this, then the next concept that I want to bring out regarding this joint density function will be what we call the marginal distribution. Alright. Now, so let's suppose if I got a random variable s, which is a vector of random variable, okay, consists of n random variable like that, okay, then of course to describe the probability distribution of it, then of course you can use the joint density function, isn't it? But sometimes, okay, instead of looking at the whole vector of random variable, so sometimes I may be only interested in studying one of the random variable. So let's say it's 2, okay. Then here the question will be, so in order to study this, then we will need the distribution of the S2. Okay, so that means I want to know, okay, so what is the likelihood that so the S2 equal to a particular value. Okay, so then here then this distribution, okay, is what we call marginal distribution. Okay, so which is basically just the distribution of a particular random variable from your vector of random variable. Okay, now then the question will be, so given this joint density function, so how would you get this marginal distribution? So I would say the idea is very simple. So to just demonstrate it, so again we will try to divide it into 2 cases. Okay, so again the first case is, so let's say this is a discrete random variable. Okay, and then of course in case if all these SI are discrete random variable, then to describe the distribution of the S1, so you can use what? You can use this probability mass function. Okay, now and then to get this probability, okay, so remember that, okay, so this event only restrict the values of the SI. Okay, so that means other random variable, let's say S1, S2, Sn, so can take any value. So that means this probability can be written as probability that Si equal to small si and S1 equal to S1 can take any arbitrary value, okay, from mass infinity to positive infinity. S2 is positive infinity, and then Si minus 1 minus positive infinity, and then Si plus 1 from minus infinity to positive infinity. Okay, something like that. Okay, now and then here, so given this, so you can try to, so given this joint density function, so you can compute this probability by computing this summation. Okay, so you just sum up all possible values of this S1 and then all possible values of S2, Si minus 1, and then summation all possible value of Si plus 1, and then summation all the Sn. Okay, so a lot of summation. Okay, so we just skip the Si, okay, because Si take a particular value, right? Okay, and then you just get this joint density function. Okay, so S1 dot up to Si plus 1. Okay, and then you add, and then you have the Si, so which is the first one. Okay, so then this is how do you get the marginal distribution function. Okay, and then similarly, if you talk about the continuous cases, so basically we do the similar things. Okay, now but here of course in order to get the marginal distribution, so what it means is, so we talk about the probability density function, But remember, for continuous random variable, if you want to get the probability density function, so you should start with the cumulative distribution function, right? The CDF. Isn't it? Now then, using this similar idea, okay, so then this is what you get. Okay, so this one is what? It's one I SI, and then SI, Sj belongs to, take any value for all j does not equal to I. Okay, then given this, so you can derive this integral through this multiple integral again. So which is so the first integral will be for the SI, and then you also have other integral which is for what? S1 up to SI. Okay, so this is school SI. Okay, and then you integrate this joint density function. Okay, so dsi minus 1 and dsi plus 1 dsn and then dsi. Okay, so sorry that we don't have too much space here. Okay, now then this is how do you get the CDF, and then if you want to get the PDF, remember, then you can just differentiate it, right? Differentiate your CDF one time. Okay, now and then here so the only term that involve the SI will be what? Will be this one, right? So that means if you differentiate this, so by the fundamental theorem of calculus, so you can just punch in the S1 to here, and this is what you get. Okay, so we don't have the BSI anymore. Okay, so then this is how do you get this marginal density function of the SI. Okay, so basically you can see the formula is very similar to the case for discrete one. Okay, so basically you just try to sum up all other possible values of the of other random variable Sj other than the Si. Okay, so just for discrete case, so you have the summation, but now for the continuous random variable case, then you have this integral. Okay, so but basically they are similar. Okay, now so here then this is so then this is the case. Okay, for so then this is for the marginal distribution. Now then the next thing related, then the next concept, okay, will be what we call the independency. Okay, because here given a vector of random variable, so it will involve will involve several random variable, right? Okay, and then as I have said before, so this random variable depending on different situation, so can be independent or maybe dependent. So here, okay, then the one important question will be, so given this random variable S1, S2, Si, okay, then how do we describe whether they are independent or not? Okay, and then to describe this independency, so first of all, just recall what we have learned in the ordinary probability course. Okay, so remember in the environmental probability, so we know, let's say if you get two events A and B, okay, so we say these two events are independent. So if and only if, so the occurrence of one event does not affect the occurrence of another event, right? So in terms of the conditional probability, that means, so let's say if the event B has happened, okay, then the probability that the event A will happen will be only equal to the probability that A will happen. So that means whenever whether or not B will happen will not affect the likelihood that the A will happen. Okay, and here remember, according to the definition of probability, so this conditional probability can be written as the probability that A and B divided by probability of B, right? So that means, okay, so this equation can also be written as well as this form, right? Isn't it? So then this is just the equivalent definition of this independency. So that means, okay, if A and B are independent, then we have this multiplication rule. Okay, now so here actually we can try to make use of this to define the independency of n random variable. So in particular here, let's say we say S1, S2, Sn are independent. If and only if so this the probability that so the S1 between A1 and B1, S2 between A2 and B2, and then Sn is between An and Bn, okay? So can be written as well, this product. Okay, so meaning that we have this product rule. Okay, so then this is how do we define this independency. Then of course in terms of the probability mass function, so that means this John density function of S1, S2 and Sn can be broken down into the product of each of the marginal distribution of the Si. Okay, so here this one roughly equal to probability Si equal to small si, and then this one is probability that S1 equal to small s1, Sn equal to small si. Okay, so this is how do we understand this independency. Okay, so here, okay, then this is how do we describe the random variable independent, so using this marginal distribution. And then perhaps the last thing that I want to say about this distribution will be what we call this change of variable formula. So basically, what is that? Okay, so the story is something like that. So let's suppose if I'm interested, so let's say if I got a vector random variable S1, S2 and Sn. Okay, so sometimes, okay, we may not just want to investigate the S1, S2, Sn itself. Okay, sometimes we may be interested in looking at some other random variable which is a function of this S1, S2, Sn. Okay, so for example, it could be let's say S1 is the sum of all these Si, okay, or maybe even something more sophisticated, something like that. Okay, etc, etc. Okay, now then of course the question here is, so given this John density function, okay, of S, okay, so which is given by this. Okay, then my question is, so is it possible for us to get the distribution of this new random variable y? Okay, then the result, okay, will be what we call the change of variable formula. Okay, now and here before I present this final result to you guys, okay, so let us try to understand this formula, okay, by working on one simple cases. Okay, so let's suppose we only get one random variable, okay, and that means one random variable, that means the S. Okay, so then we let the fss be your probability density function, or maybe probability mass function if you like. Okay, now and here let us consider this new random variable, which is a function of GS. Sorry, it should be capital letter S. Okay, now and here we will try to find, so what will be this probability density function of y. Okay, now and here, okay, to just make the things to just make the things less complicated, so I just first of all assuming that so this is a, so both x and y are continuous random variable. Okay, and then another thing is we will assume that so this gs is continuously differentiable. And is straightly monotone. Okay, meaning that it is either straightly increasing or straightly decreasing. Okay, so now and here let's say if I really want to get this PDL of y, so remember the first thing that you should do is you should consider the CDI, right? Isn't it? Now and then the things here is, so to get this probability, so because in our hand we only know the PDL of S only, right? Okay, so that here, so in order to derive this probability, then you need to try to transform this probability from y to s. Okay, so that means here in order to get this, so you have to know what values of s will give you this y less than or equal to small y. Okay, then to do that is not that difficult. Okay, so then we just try to draw a graph. Okay, now so remember that okay, so this function gs is straightly monotone, meaning that it is either increasing or decreasing, right? Now so here let us assume that so the g is increasing first. Okay, then in that cases, then your gs is something like that. Okay, now and then here, okay, so we are looking for y smaller than small y, right? Isn't it? Now then here, then let's suppose the y is somewhere here. Okay, now then because it is straightly increasing, then for each of values of y, so you can find the corresponding values of s, right? Such that the gs equal to y. Then we let it to be what? The inverse of y, isn't it? So here, okay, then if you want to have what? Y smaller than small y, and that means what? Your s has to be less than g minus y. Okay, so then that is this is what we get. Then the next thing is so to evaluate this probability, then this probability will be equal to this integral from minus infinity to g inverse y. Okay, and then you got fss and then ds, isn't it? So then this is the cumulative distribution function of y, right? Okay, then here if you really want to get the PDF, so you just simply differentiate this CDF one time. Okay, now then to differentiate this, so remember, okay, so you first, and then here, so the only y involved is this upper bound of your integral. So by fundamental theorem of calculus, so the derivative of this guy will be equal to fs g inverse y. Okay, and then because you have this, so because this is a function of g, right? So remember, according to the chain rule, so you have to differentiate this. Okay, now and then how do you differentiate this inverse function? Okay, so here, okay, actually to get this is not that difficult. So let me try to let the set to be equal to g inverse y. Okay, and then you can just take the g on both sides. Okay, then the next step is you differentiate both sides with respect to y. Okay, so that means, okay, so for this side you differentiate this and then d set over dy, and then this is equal to 1. Okay, and so that here by putting this to the right hand side, okay, then this is what we have. So remember, set is just equal to g inverse y. Okay, then this is how do you get your derivative, so which is equal to 1 over g prime G inverse Y. Okay, so then this is what we have, okay, for the increasing case. Okay, and then of course similarly, if you instead of having the increasing function, so let's say if you got the decreasing cases, okay, then actually the calculation will be very similar. Okay, so here, okay, let's suppose if you got this is so decrease, so the GS is decreasing. Okay, so actually you can try to get the PDF using a similar method. Okay, so which is equal to the probability that y less than or equal to y, and then probability that g is less than or equal to y. Okay, and here because your function now become a decreasing function. Okay, so if you want to have g is less than y, then that means what? You need to have the s to be greater than g inverse s. Okay, so that means that the s has to be greater or equal to g inverse y. Okay, so this was equal to y. Okay, now and then here to get this you get this thing. Okay, so you now integrate that using this new formula. Okay, now and then again, in order to get this PDF, then you just differentiate one time. Okay, and then and then this time, okay, when you substitute the g inverse y into that, okay, remember this g inverse y now is at the lower bound of the interval, so that means when you put it into that, then you will have the minus sign, and then again, then you also differentiate this g inverse y as well. Okay, so then this one again equal to what? 1 over g inverse y. Okay, and then here, okay, so then this is what you get, and then because the g is decreasing, so meaning that this g prime is negative. So if you combine this minus sign and this g prime, so actually this formula can also be written as this. Okay, so 1 over absolute value g prime g inverse y. Okay, so then this is so then this is the formula. Okay, now and then here, so then this is what how do we get the probability density function of a function of random variable s using this very simple method. Okay, so here actually you can try to extend this method to a general cases. Okay, so let's suppose you got a vector random variable s1 s2 sn. Okay, and here let's suppose, okay, I got a vector random variable y, so which is a function of this n random variable. Okay, and then here so again, okay, so each of these gi, okay, are continuously differentiable. Okay, and then here we will, so here, okay, we will also assume that so the Jacobian matrix is so the Jacobian matrix, so which is the determinant of this matrix. Maybe I writing a better way. Okay, so which is the collection of the partial derivative of all these function g respect to each of the variable x1, x2, xn. Okay, and then we assume that this one is not equal to 0. So basically, this condition is very similar to the earlier assumption that G is monotone. Okay, because in order to get the probability distribution of y, okay, so remember in the single variable case, so one crucial step is, so you have to know, so given that, okay, y less than or equal to y, so you have to know which value of s will give you the gs less than or equal to y, right? Okay, and then remember at that time, so we have to try to make use of the inverse function and do the job. Okay, so then that means that, okay, so if you want to get your PDF using this procedure, then you have to guarantee that this inverse must exist. And then mathematically, then that means you need to have this sort of one-to-one nature. So in the sense that you don't have two s mapping to the same number. Okay, so that's why we assume that, okay, so the G has to be monotone in order to have this pattern. Okay, and similarly, if you have a function of multiple random variable, so in order that, okay, you have this inverse exist. Okay, so we will assume that, so this Jacobian matrix must be non-zero. Okay, so that by inverse function theorem, then you can try to write the S. Okay, as well as the inverse, okay, as the function of this y1, y2, yn. Okay, so here, okay, so then this h1, h2, hn are just what? The inverse function. So a kind of inverse function, okay, somewhat representing this inverse of this. Okay, so here, okay, then this is what we get. And then here, let's say if you have this happen, so actually you can try to extend this formula. Okay, try to extend this formula, okay, to a to these general cases. Okay, so in particular here, and if you have this n when random variable, okay, and this so just recall for one variable cases, so we have this, right? Okay, f y equal to f s g inverse y. Okay, and then 1 over the absolute value, and then g prime, okay, and then g inverse y, right? Okay, so then this is a one-dimensional cases. Okay, and then actually you can try to extend it to n-dimensional case as follow. Okay, so here, okay, then the joint density function of this y, okay, can be written as fs, and then h1, and then y1 yn, and then s2 y1 up to yn, and then hn y1 up to yn. Okay, and then 1 over this determinant 1 of this absolute value of y. Okay, so here so how do you understand this extension? Okay, so here the first term, okay, it's just like what? The first term in the one-dimensional cases. Okay, so which is the joint density function of S. Okay, and then you evaluate at this inverse of this y1, y2, yn. Remember, h1, h2, hn is just your inverse. Okay, so same as this. Okay, and then so the second term will correspond to what? Correspond to this, right? So remember, for one-dimensional cases, so the denominator is just what? The derivative of g respect to the derivative of g. okay, the absolute value. And then for n variable case, so then this j again is just what the first derivative. But just like here, because you have n function, you have n when you have n variable, so that it now become a this matrix. Okay, and then we take the determinant. Okay, and then again we take the absolute value. Alright, so here, okay, then this will be what the general change of variable formula. Okay, now of course for the proof, so actually it will involve some knowledge in multivariable calculus. So that is what we call the change of variable technique. Okay, but just like here, I guess I'm not going to go through that. Okay, because it may be a little bit tedious. Okay, so here to just give you a little bit to give you some idea about this formula. So let us just show you one example. Okay, so here let's suppose I got S1, S2 two random variable. Okay, sorry, and then each of these SI has exponential distribution. Okay, with the mean theta I. Okay, so that means that your PDF is equal to this number. Okay, and then here, so let's assume they are independent as well. Okay, and then here, so I'm interested in looking at the random variable y1 and y2. Okay, so which is given by, for y1 that will be equal to s1 plus 2s2. Another one is s1 minus s2. Okay, and here what I want you to do is, so I want you to get your Jordan density function of y. Okay, now so here in order to get this, okay, so basically we just use this change of variable formula as we shown above. Okay, so let me just get that. Okay, and then 1 over this j. Okay, and here, okay, so remember this j is your determinant of your Jacobian matrix, so which is G1 S1, G2 is G1 S2, G2 S1, and then DG2 DS2. Okay, now and then here in order to get this PDF, so what you need to do is just to get all this detail. Okay, so here here let us try to do that one by one. So first of all, you first try to get your PDF. Okay, I mean the FS. Okay, so here, okay, remember this is what the Jordan density function of S1 and S2, and then each of these SI has an exponential distribution, right? So here, okay, according to the dependency, so that means the Jordan density function of S1 and S2 is just equal to the product of the PDF of SI, right? Okay, and then here each of them has a exponential distribution, so they have this PDF. Okay, so that's this one will be equal to 1 over theta 1 theta 2. Okay, then that will be our PDF. Okay, now and then here, so this is the first step, and then of course the second step will be what will be the Jacobian matrix. Okay, now so here, okay, how do we get this? Now so just remember y1 y2 is equal to s1 plus 2 s2 and then s1 minus s2, right? Okay, so which is this one will be what your g1 s1 s2, and then that one will be your g2 s1 and s2. Okay, so in that cases, okay, so you can get your determinant easily. Alright, so here, so if we differentiate the G1 with respect to S1, okay, so that means you differentiate this one, right? So you only get 1. And then for the second one, so you differentiate with respect to G2, then you got 2. And then for the second row, you differentiate the G2, okay, with respect to S1 and S2 respectively, and you get 1 and minus 1. Okay, then just a little bit calculation, then you find that the J equal to minus 3. Okay, so then that you got the second one as well. Okay, then finally, then you just need to get your inverse function. Okay, so here, okay, given that your y1, y2 equal to this guy. Okay, then our goal is I want to get so we want to express the s1, s2 in terms of y1 and y2. Okay, so here then basically you just need to solve this equation for the s1 and s2. Okay, and then so you just try to solve for this s1 and s2. Now, and then to get this, so first of all you can solve for the s2 first. Okay, so that means that you try to subtract the second equation from the first one, 1 minus 2. Okay, then you will get y1 minus y2 equal to 3s2, which means s2 equal to y1 minus y2 divided by 3. Okay, and then once you have that, then you put it into the second equation. Okay, so that your s1 will be equal to what? Equal to y2 plus y1 minus y2 over 3. Okay, so which is equal to y1 over 3 plus 2y2 over 3. Okay, so then this will be what? Your inverse function of the first inverse function, and then this is your second inverse function. Okay, then here once you have all this ready, okay, so then you can now try to punch it all this thing, okay, into this final formula. Okay, then you can easily get the final answer. Okay, so here let me try to just briefly do that. Okay, so here fyy equal to fs h1 s1 and y1 and y2. Okay, and then 1 over absolute value of j. Okay, now so let's just pick up the detail. First of all, for the j, so it is equal to minus 3. So meaning that after you take the absolute value, so this one will give you 3. Okay, now and then for h1, so that will be y1 over 3 plus 2y2 over 3, and then for h2 for h2, so that will be y1 minus y2 over 3. Okay, now and then the next thing will be just your fs. Okay, so remember your fs is equal to this one. Okay, so you can just put that in. Okay, and then you substitute the first one into the first entry. Okay, and then minus y2 over 3 divided by 3 to 2. Okay, so then this is basically what you get. Okay, then you just rearrange your term, then you can get your probability density function of this new random variable y1 and y2. Okay, so here then this is how do we make use of this change of variable formula. Okay, so here, okay, then basically, so this is just some basic theory about the probability distribution of a vector random variable. Okay, so first of all, we have the joint density function, and then followed by the marginal density, and then we also have the independency, and finally, this very important change of variable formula. Okay, now, and then after this probability distribution, then then the next thing that we are going to do is about the expected value and the variance of a vector of random variable s. Okay, now so remember, given a random variable s, so which is the single one. Now besides the probability distribution, so of course you can talk about what the expected value, right? Okay, so we should try to tell you the average value of s. Okay, and then another one, okay, will be what? The variance, right? Isn't it? And here, actually, given this vector random variable, so you can try to define these two concepts in a similar way. Okay, so then the idea is something like that. So let's say if you want to get the expected value, okay, then you can try to define the expected value of a vector of random variable just equal to what? Equal to the vector of expected value of individual random variable. Okay, so meaning that, okay, so you just take the expected value of each of these random variable. Okay, so then this is a fair way to define this expected value. Okay, now then perhaps the next thing is, so then how about variance there? Okay, now so remember the variance of a random variable s, so try to measure the fluctuation of s around the expected value, right? Okay, now of course here we can also try to define this variance in a similar way, but just here this is not good enough because remember, given a vector of random variable, so this random variable is also may depends on each other. Okay, meaning that, okay, the movement of one random variable may affect the another, right? So then that means it will also affect the overall fluctuation. Okay, so here in order to do this, so it seems like that if we want to talk about the variance of a vector of random variable, so besides this besides the variance of the individual random variable si, okay, so we also need to study so we also need to capture the correlation between two random variables. Okay, and then remember in the environmental probability course, so we can try to measure this dependency using this covariance, right? Isn't it? So then that means if we want to define the variance of vector random variable, so you need to include these two things. Okay, so that's the reason why here then we try to develop the concept what we call covariance matrix. Okay, so which is what? Just a matrix which try to collect all the covariance of this form. Okay, so the first row will collect the covariance of Si with other random variable, okay, including itself. Okay, and then the second row will be what? The covariance of the random variable S2 with other random variable. Okay, so then this is the covariance matrix which collect all these covariance. Okay, and here, okay, just remember now if you look at the diagonal entry, okay, so you have the covariance of s, so we have the covariance of si with the si itself, right? Okay, so remember according to the definition, so if you have two identical random variables, okay, so then the covariance will be just equal to what? Equal to this, right? by definition. Okay, and then because these two are identical, right, so that will be equal to this one all square, and then this one essentially just the variance. Okay, so then that means this diagonal entry is just a variance. Okay, so here, okay, then this is the structure of this covariance matrix. So you can see, so this matrix collect all the variance of the random variable as well as the covariance. Okay, then we will try to use that to record the variance of a vector or random variable. Okay, now and then here, okay, so this is the expected value and the covariance matrix. Okay, now and here let us try to discover a little bit property about this expected value and the covariance matrix. Okay, now so first of all, so let's talk about expected value. Now remember one property about the expected value is, so if you have a random variable s, so if you talk about this linear combination, okay, so which is as plus b, okay, so then you can see, so this one should be equal to this guy, right? Is it? And then of course, and then here similarly, if you have a vector of random variable s, so actually you will also have the similar result. Okay, so let's say, okay, if you got a vector of random variable s, so which is something like that. Okay, then here if you have a matrix A, so if you consider this as plus b, okay, so here the A can be a m times n matrix, okay, and then the b is m dimensional vector. Okay, then if you have this as plus b, so actually you can write that as this as well. Okay, so then basically, so we have the similar property as we have for the single variable case. Okay, so you can take out this constant matrix out, okay, and then you take out this fixed vector b. Okay, so then this is the expected value. Now then the second one definitely will be the variance. Okay, now so remember, if you have a single random variable case, so you have this property about the variance, right? So let's say if you have the variance of as plus b, okay, then here and then here, okay, so this one will be equal to what? Equal to a squared and then variance of s, right? Okay, so then this is the property of the variance. Okay, now and this here, how about the case, okay, if you have this vector of random variable, okay, now so here, okay, to just facilitate the presentation of the formula, so here given this random variable s, so I let the covariance of s, okay, be my covariance matrix. Okay, so which is this omega. Okay, and then so let's say, okay, if you got what the covariance of as plus b, sorry, so let's say, okay, if you got the covariance, so a s plus b. Okay, so similar setup as we did earlier. Okay, then actually, so we will have the similar results. So this one, it will be equal to a and then covariance of s vector and then a transpose. Okay, so essentially this one is very similar to that. Okay, so what you need to do is, so first of all, you remove the b because the b does not affect the variance, right? And here and then you have the a multiplied in front of that. Then when you consider variance, so you need to multiply this a twice, right? And then here actually for n-dimensional cases, so we have the similar result. So you just need to multiply your covariance matrix by a twice as well. But just here we don't have this a square covariance s, okay? But just we will multiply the s 2 times in this way, okay? Now, and then the next question will be so so how do we establish this, okay? Now then to establish this, so first of all, so to establish this formula, now then the first thing that I will do is, so first I will get another useful formula for this covariance, okay? Now so remember by the definition, so the covariance matrix is something like this, right? It's the covariance of all this combination of this Xi and Xj. Okay, now and then here remember this one is just equal to expected value of S1 minus expected value of S1. Okay, so then this is just another way to present this covariance. Okay, so but just through the definition of the covariance. Okay, and then here remember, so actually this matrix can be written as the expected value of these things. Okay, so then this is so actually this matrix can also be written as this vector product. Okay, so of course if you want to load this, so you just recall that. So let's say if you have two vector like this, okay, so one is a1 a2 an in a column, and then you have a1 a2 an in a row like that. If you multiply this, so you will get a1 times a1, a1 times a2, and then a1 times an, and then a2 times a1, a2 times a2, a2 times an. Then you have something like this. Okay, so here actually, so this equation just follow from this simple facts in the linear algebra. Okay, now and then here, okay, so given this, then you can try to write this in vector form. Okay, so this one will be S vector minus expected value of x vector. Okay, and then this one will be x vector minus expected value of x transport. Okay, so they are essentially, so these two are essentially the same, right? Okay, now and here so this is another way to get this covariance matrix. Okay, now then here then as well try to use this to prove my theorem. Okay, now so here, okay, then let's start with AX plus B. Okay, now then here to get this covariance, so you just use this formula. Okay, because this is applied to any vector of random variable. Okay, so that this one will be equal to AX plus B. Okay, now so it looks complicated, but first of all, because the B is space, right? So then these two can be cancelled out. Okay, so then you got this, and then here because you have the A as a common factor, so you can also take that out. Okay, then this is what you have for the first one, right? Isn't it? And similarly for the second one, so you can also do the same thing. Okay, now then the next thing is so how do you move on? Now so here, okay, when you take the transport on this product of this two matrix, so it will be what? Just equal to this. Okay, so you will that two things. Isn't it? Now, and here the next step is, so here because the A is a constant, so you can take that out from your expected value. And then the remaining stuff, so which is the expected value of this way, actually it is just a covariance matrix. So that this one will be equal to this. Okay, so we are done. Okay, so here then this is so then this is the some property about the covariance matrix. Okay, now and then so after this, okay, then actually we have developed this basic theory regarding this vector of random variable. So the distribution function, expected value, and also the covariance. Okay, now and here before I stop this tutorial, okay, so the last thing that I want to introduce is just one special distribution of vector of random variable, so which is what we call multivariate normal distribution. Okay. So of course, just like the case for the single random variable, so of course we can have a different special distribution defined on the vector of random variable. Okay, and then one popular distribution that we use. Okay, so it's what we call multivariate normal distribution. So basically, so you can regard this multivariate normal distribution as extension of normal distribution, okay, which you have learned that in your environmental probability course, right? So remember, we say it's follow this normal distribution with mean mu and variance sigma square. So if and only if, so So if the PDF is given by that, right? Okay, so then this is the what we learn about this normal distribution. Now, so here then how do we define this multivariate normal distribution there? Now, so to do that, so what we do is, so we will try to develop a alternate definition of this normal distribution. Okay, now so here just recall, if you got the S follow the normal distribution. Okay, then if you consider this standard score. Okay, so it will follow the standard normal, isn't it? Now, and then here, so given this formula, then you can rewrite the S as in terms of set, right, which is the mu plus sigma set. Okay, and the set follow the standard normal. Okay, so then this is well another representation of a normal random variable, so which the S can be written as well as the mu as a some constant plus sigma times a standard normal random variable. Okay, and then using this, then you can try to define the multivariate normal distribution as follows. And then to define this, so first of all, okay, we call from the normal distribution, so it involves the standard normal, right? Okay, and then of course here, if you have n random variable cases, okay, then we will try to define this vector set as the vector of standard normal random variable. Okay, so in the sense that each of these follow the standard normal, okay, and what's more, so they are independent. Okay, now then given this, then now you can say, okay, so let's say you got a vector of random variable S, okay, then we say S follow this multivariate normal distribution if and only if it can be expressed in a form of which is similar to this. Okay, so in particular it can be written as this. Okay, so this one is not A, this one is not Z. Okay, so meaning that it can be written as some forms of mu plus A Z. So which is what essentially identical to what you have for the single variable case. Okay, so here then this is what how do we define this multivariate normal distribution. Okay, now and then the next thing will be what is about the detail of this multivariate normal. Okay, now so remember that given a normal distribution, so there are two parameters, right? One is the mean, another one is the variance. Okay, so you have these two parameters. Okay, and then similarly, if you have the multivariate normal, so basically you also have two parameters as well. So the first one definitely will be the mean, right? Isn't it? And then the second one will be what? The variance, okay? And then of course for the case if you have a vector random variable, remember we use the covariance matrix. Okay, now then the question here is, so then what will be this mu and this sigma? Okay, now and then to get this, it is not that difficult. Okay, so let's say if you want to get the mean, which is your expected value, so then that will be what? Equal to expected value of mu plus a set. Okay, and then here according to the property of expected value, so that will be equal to the mu plus a times expected value of set. Okay, now and then here remember Z represent what? The vector of normal, standard normal, right? And the mean of all these Z are equal to 0. So that means if you So that means if we consider this as expected value, it will be equal to 0, 0, the loss 0, right? Okay, so then that means all this guy will be 0. So that the expected value will be equal to mu. Okay, so which is equal to this. Okay, now and then another thing will be what? How about covariance then? Okay, covariance matrix. Okay, now and then here using the property of this. So here remember the S is can be written as well some constant vector plus a constant matrix times the vector one variable set, right? Okay, then according to the property of the covariance, so this one equal to this way. Okay, and that one equal to what? A of covariance matrix set and then times A transpose, isn't it? Now, and then what is that? So then what is this covariance matrix of set? Okay, now remember, this covariance matrix set is just equal to the covariance of Z1, Z1, Z2, Z1, Z2, right? Something like that. Okay, now and then here remember, because all these Ezi are independent, okay, they are independent standard normal. So that means this covariance, okay, will be equal to 0. Okay, all the off diagonal. Okay, but just here, if we talk about the diagonal entry, okay, so remember each of these covariance is just equal to the variance of the Z1, Z2, Zn. Okay, and remember they are standard normal, right? So that means the variance is equal to 1. Okay, so then that means this covariance matrix will be a kind of identity matrix. So that's why this is what you get. So you get A and then a identity matrix and an AT. And then remember in matrix multiplication, so the identity matrix is just equal to 1, right? So then that will be equal to AAT. Okay, so here then this will be what our covariance matrix. Okay, so which is what equal to A times AT. Okay, so here I would say this one will be what also similar to this. Okay, because what here, okay, remember so the variance of a single normal random variable is sigma square, right? So which is what just the square of this constant. Okay, and then here for the multivariate cases, so we have similar phase. So the covariance is just what the square of this constant A. Okay, but just what we don't do that in A square. Okay, but just what we will do that in by multiplying the A by the transpose of A. Okay, so here this is the basic information about this multivariate normal distribution. Okay, now then of course here given this multivariate normal, then there are lots of properties that you can discover. Okay, now so here okay, just to not to make the things complicated. Okay, so I will just list out some important property. Okay, so the first property definitely will be about the John density function of this multivariate normal. Okay, so the thing is, so let's assume that the S follow the multivariate normal. Okay, so here, okay, so I will use this notation to denote that. Okay, so this one stands for, sorry, this one stands for multivariate normal. Okay, distribution with the mean mu, okay, and the covariance matrix sigma. Okay, then the first property is so the John density function of S will be given by this formula. Okay, and here, okay, so the x vector is just equal to x1, x2, xi. Okay, so then that will be the general formula for this joint density function. So I would say it looks rather complicated, but actually it is parallel to the one for the single variable case. So remember, for single variable, so the PDF is something like this. And then you can try to write this slightly in this way. Sorry, I missed the 2 here. Okay, and then you got S mass mu, and then sigma 2, and then divided by 2. Okay, and then here, okay, so by writing this PDF into this form, so actually you can see, so these two are essentially similar. Okay, so first of all, your sigma, your variance, okay, sigma square, will be replaced by what? The covariance matrix. Okay, and here, okay, and here, okay, so for the first term here, so when you replace the sigma square by the sigma, okay, then we talk about this determinant. Okay, and so here, okay, then you can see, so these two are the structure of these two PDF are very similar. Okay, but just we extend it from a number to a vector. Okay, and then here, if you really want to prove this, so basically you can use the change of variable formula and do the job. Okay, so the idea is something like that. Okay, so remember the S is so remember by definition, so the this random variable S can be written as mu plus AZ, right? Isn't it? So and then which is equal to what? mu1, mu2, mu(n), and then plus a11, a12, a1n, a21, a22, a2n, an1, an2, ann, and times this, right? Okay, then of course you can also try to write that as well. Write that as mu1 plus a11 z1 plus a12 z2 a1n zn. Okay, so here you can see, so all this so this s is just what? A function. So here by writing this, so you can see actually this s is just what? A function of this random variable z1, z2, zn. Okay, so here, okay, then by taking this one as your g1, this one as your gn. Okay, then you can use the change of variable formula to get your PDF of your random variable s. So first of all, you first try to find your PDF, the joint density function of your vector random variable set. Okay, so which are what? Standard normal independent, right? So you got the PDF. And then the second thing is, so using this to get the change of variable formula, then you get the PDF of s. Okay, so here I'm not going to show the details, okay, because it's a little bit messy. Okay, but the idea is it's not that difficult. Okay, now, so here this is the first property. And then as well try to look at another one. So another property will be something also very important is about some linearity about the normal distribution. Now remember in the one variable case, so let's say if you have the S as having the normal distribution, then if you consider another random variable which is A plus B, so it will follow the normal distribution with mean A mu plus B and then the variance A squared sigma squared, right? Okay, so here actually we have the similar result for the multivariate normal. So let's suppose you got a vector of random variable which follow the multivariate normal with the mean mu and then the covariance matrix sigma. Okay, and here if you consider this linear combination, so actually it will if you consider this a combination, so where the A is what m times n matrix and then the B is the m dimension vector. Okay, then actually we can show that so this one will also have the multivariate normal distribution. Okay, now and here because it is a m dimensional vector, so that means this will be a m multivariate normal. Okay, and then with the mean equal to A mu plus B and then the covariance matrix of that. Okay, now and here in order to prove this, so actually is not that difficult. Okay, so basically you just will use the definition of multivariate normal and do the job. Okay. So to start with, so remember the S follow the multivariate normal, right? So then that means that S can be written as mu plus some constant matrix C and then a vector of standard normal. Okay, and this C will satisfy CCT equal to sigma. Okay, now and here in order to show the AS plus B follow the multivariate normal, then you just need to argue that it can also be written in the form which is similar to this. Okay, now then this is what I do. So let's take AS plus B. Okay, and then you punch in the S inside. Okay, then the next thing is then you try to rearrange the term. Okay, so you got A mu plus B, okay, and then plus AC set. Okay, now and then here if you try to take this one, okay, this term, okay, as your new mu prime, okay, and then this constant, okay, as your new A prime, okay. Then actually, so this AS plus C will follow the multivariate normal, right? Okay, and of course here the mean will be what? A mu plus B, so which is equal to that. Okay, and then if we talk about the covariance, so that will be what? The new covariance, so let's call it sigma prime, will be equal to A prime times A prime transpose. Okay, so that will be equal to AC times ACT, and then transpose with CCA. Okay, and then this one CCT equal to what? The sigma. So that's why you got that. Okay, so here then this is the second property about this multivariate normal. Okay, so that means if you have S as a multivariate normal, then AS plus B is also a multivariate normal as well. Okay, so here then this is the so then this is the second property of multivariate normal. Okay, and perhaps one one more important property, it will be something like that. Okay, so here let's suppose, okay, you got two random variables S1 and S2, and then each of them follow the normal distribution. Okay, and they are independent. Alright, and then this property try to say that, so we will try to put these two random variables together, okay, and form this vector random variable S1 of this vector random variable S, okay. Then here, because both of them follow the normal distribution, right, then we will expect that the S will follow sort of normal distribution as well. So here, this property try to say that, so if these two random variables are independent, so this S1 and S2 will follow the multivariate normal, okay, and then with the mean mu and then the covariance matrix sigma, okay, and here the mu will be what? Will be just mu1 and mu2, okay. The first one will be the expected value of S1, mu2 will be the mean of S2, okay, and then for covariance matrix, so that will be sigma 1 square, sigma 2 square, and 0, 0. Okay, here remember the diagonal entry is just what? The variance of S1 and S2, and then the off diagonal is covariance of S1 and S2, and because they are independent, right, so we expect that it should be 0. Okay, so here then this is the third property, okay, about this multivariate normal. So if you have two normal random variable which are independent, if you put them together, it will follow the multivariate normal. Okay, and of course this can be extended to a general cases. So where the S1 become a multivariate normal and this one become a multivariate normal. So these two put, if you combine these two together, it will also follow the multivariate normal as well. Okay, now and then the proof of this so will be a little bit complicated. So you have to use the you have to argue this, okay, using the joint density function of the multivariate normal. Okay, so I guess I'm not going to present that here. Okay, so here basically then these are the three property about this multivariate normal distribution. Okay, so which will be essential for you to learn some further theory related to the maximum likelihood method. Okay, now so I guess then that's all about this tutorial. Okay, now of course here we are not going to really go through every detail, okay, including the proof. So of course if you are interested in knowing the theory about this, so you can take a look on some textbook in which is related to the multivariate analysis. Okay, so actually all these, okay, are just the basic theory, some basic theory that will cover in this area. So you can try to find those reference book and try to study this. Okay, now anyway, so then I guess then that's all about this tutorial, and hopefully you get, after this tutorial, then you have some rough picture about the theory of the rectangle random variable as well as the multivariate normal distribution. So I guess that's all for today, and have a nice day.